Thanks, John and Cody, for putting together this very nice summer seminar series, which continues after summer, so that's nice. And giving me the opportunity to speak here. So indeed, I will present my work on 6D anomalies on the circuit and F-theory implications. So this is work based in this paper from May. So let me start with basics about anomalies in 6 dimensions. So because 6D is an even dimension, you can have local anomalies due to chiral fermions, just like in the 4D case. In the 6D case, it's the anomaly is proportional to the force power of the charge, as can be seen from most directly from the box diagram, which is the analogous from the triangle diagram of the usual 4D, the usual 4D case, but for 6D. So here, just to set up I'm just considering a single chiral fermion of charge Q under an abelian gauge field. I put hats on everything to say it's in 6D, because later on we will be working in 5D as well, once we compactify. But because of this power 4, we cannot add several fermions such that the charge cancel. The force power of the charge cancel. This is unlike the 4D case, where you can add, because the anomaly goes like the cube of the charge because of the triangle diagram, you can add several fermions which have charges such that the anomaly vanishes, just like in the standard model. But in 6D, you cannot do that. So in 6D, you need to invoke the Green-Schwarz mechanism. So you add to the action this Chern-Simons coupling, where B is a two form, which are naturally present in 6D. And if the two form varies like this, then this term is not invariant. And it will cancel the one loop variation if you require this condition to hold. And diagrammatically, it's a 3-level diagram that cancels the box diagram, which is so. So you have a classical piece, the Green-Schwarz piece, which cancels the one loop piece, the one loop variation. So this is very peculiar. This will play a big role. Okay. So now we want to ask the question: what if we don't consider a 6-dimensional space, but with one of the direction being compactified? So and ask what is the effective theory on the 5-dimensional space? What will happen to the anomaly in this case? So we looked at this question 3 years ago with Thomas Grimm and Diego Regalado for the 4D situation. And then we saw that if you started with a 4D theory, which is anomalous, and put it on a circle, then the 3D regularization you use to compute the one loop action in 3D, it does matter which regularization you use. But we also saw that if the 4D theory was anomaly free, meaning that if you add a bunch of fermions which have the sum of the cubes of the charge which cancel, then the 3D regularization does not matter. And then you could say, I don't care about anomalous theory, I just care about anomaly-free theory, so why should I care about the regularization? But we just saw that in 6D, you need to cancel this one loop variation with a classically known term, the Green-Schwarz term. So in a sense, it's like if it's an anomalous theory, always. So you always expect that the regularization does matter. And we will see this in more detail later on in this talk. So this is what we are we want to look at. And this will have implications for F-theory on Calabi-Yau threefold. So since this gives you a supersymmetric theory, let me directly switch to supersymmetric theory. And in particular, a 1,0 theory, so minimal amount of supersymmetry in 6D. So you have the gravity multiplets, a bunch of tensor multiplets, vector multiplets, and hyper multiplets. The gauge field lie in the vector multiplets, of course, and we will take them for simplicity to be abelian and denote them AI. The charge fermions under the gauge field all lie in the hypers, don't have to be all the hypers, so a subset of them, which I denote N star, is charged with charge QIF. I for the gauge field I, and F for the type of fermion that labels the charge fermions. So in this language, the anomaly will be proportional to this quartic guy. And then the two forms which are required for the Green-Schwarz mechanism They lie in one in the gravity multiplets and one in each tensor multiplet. So you have nt plus one of them. So the Green-Schwarz term generalized to this term where the dot means contraction with this SO1, nt metric. And then the anomaly cancellation condition, which we had before, now it not takes this form, where this bijkl is the just a shorthand notation for the symmetric product of two b's. So this is the pure gauge anomaly cancellation condition. But in supergravity theory, you have other type of anomaly, the mixed type anomalies, and the pure gravitational one, because we are in 6 dimensions, so 4k plus 2. And these are the conditions that the theory also needs to satisfy for it to be anomaly free. Where here A is the gravitational Green-Schwarz coefficient, so in front of this term. So if a theory with only, so we are looking only at abelian gauge field. If it satisfies these 4 equations, it's anomaly free. And if it does not, it's not. Then if it's anomaly free, you can write an action, which is the following. And here you see the kinetic terms, and here the Green-Schwarz term. And the goal is to take this action, so generic C1,0 anomaly free theory with only abelian gauge group, and reduce it on the circle. So let me set up the notation. I start with the 6D gauge field, and it gives me a 5D gauge field and a scalar. So these zetas are the Wilson lines, the scalars in 5D. And A0 is the graviphoton. Similarly for the two forms, they gave me a 5D two forms and a 5D vector. But in 5D, I can dualize the two form into a vector. So I can go to a frame when I have only vectors. So let's do that. And let's also, because we are interested in anomalies, only look at Chern-Simons terms. Then if you do the classical reduction, you get the following Chern-Simons terms. The first line is gauge invariant, so nothing weird. But the second line, you see the Chern-Simons terms, which are these A wedge F guys, they depend on the scalar zeta, all of them. So this means that they are not gauge invariant. And this might sound weird, but actually it's completely normal because it's just a classical reduction of the action which had Green-Schwarz terms. And we saw the Green-Schwarz terms are classically non-invariant. So we only expect the theory to be invariant once we include the one loop correction. So we expect that once we include one loop correction, this guy will disappear. And we will do that later. But first, let me comment on supersymmetry, because we still have a superchoice, so we expect n equal 1 in 5D. And we expect the action to be able to, that can be written in the canonical form, which is this one, which is given in terms of this a prepotential f, which is a cubic function on the coordinate. So the phi are the canonical coordinates. And this ki, jk are integers, which give you the Chern-Simons coefficient. And the metric for the kinetic terms is given in terms of this f as well. So the supersymmetry relates the metric with the Chern-Simons. But this form, if the k's are integers, this form is supersymmetric, is gauge invariant. So because we had non-gauge invariant terms, we don't expect to be able to cast it in this form. Nevertheless, you can come close to that by defining the following coordinates. So in terms of what you get by the circle reduction, and defining the following prepotential. So the two first terms are cubic, so they give you the gauge invariant Chern-Simons terms, but the last term is quadratic. Well, it's not cubic. It's still homogeneous of degree, but it's not cubic. And this is what gives you the field-dependent Chern-Simons terms, which are not gauge invariant. And you see it has the anomaly coefficient in front of it. So this is to be expected at classical level, as I said, but at one loop, once we include one loop correction, we expect, we hope that this is going to go away and we will get a prepotential which is cubic. So let's do this. Let's compute the one loop corrections that can induce Chern-Simons terms. So in 5D, Chern-Simons are induced by this kind of diagram, triangle diagrams. with three gauge field as external legs. And in the loop can run spin 1/2, spin 3/2 fermions, and two forms. So just to set, to give the canonical example, if you have in the loop at spin 1/2 that runs with mass m and charge q, it generates Chern-Simons terms a wedge f with coefficient proportional to the cube of the charge and the sign of the mass of the firm. Then you can repeat the analysis for a spin 3/2 and tensor, and this is done in this paper. So in our setup, we have to distinguish two cases. If all the external gauge field are the copies of the KK photon, then because all of KK modes are charged under the graviphoton, then all of them can run. So the spin 1/2, spin 3/2, and tensor run in the loop. But if one of the external gauge field is one of the U1s, only the charge hyperenes run in the loop. Okay, so we put all this together using the result, and we find that we sum over all KK modes, all massive modes, and we find the following one loop Chern-Simons. So here I didn't put the wedge for compactness, and the coefficients are divided by these sums. You see a sum over all the KK modes with the sign of the mass of the modes that run in the loop all the time. So we have these sums over all integer, which are ill-defined. So we need to regularize it. Then you can, the often used regularization in the literature is the zeta-function regularization. Gives you a finite result directly. The first bit is properly quantized, but the last bit for each term depends continuously on the VEF of these scalars, which parameterize the Coulomb range. So this is bad if it's not properly quantized. The theory will not be invariant under large gauge transformation. But you see that these not quantized terms all are proportional to the quartics of the charge. So it smells like the anomaly. Nevertheless, this is not satisfying because if you use this coefficient in the Chern-Simons action, it will be invariant under small gauge transformation in 5D and shifts of the scalar. But we know from 6D that this should not be the case, because the 1 pi effective action should vary. It should cancel with the Green-Schwarz term we had earlier. This is what I stressed at the beginning. So something went wrong, and what went wrong is to use the zeta function regularization, because the regularization takes place in the UV. And in our case, the UV is not 5-dimensional, but 6-dimensional. So we should use a regularization that preserves 6D Lorentz invariance. For instance, one can start from 6D polyvillars and then reduce it on the circle. And if you do this, use this different regularization, you get a different result. So very similar to the previous one, but it differs in 2 points. First is the full scalar field that appears, not just the coefficient, not just the VEF, and also the coefficient have changed. So I highlighted in red the ones that changed. And these two changes are precisely what makes the result vary exactly as expected under small gauge transformation and shift of the scalars. So we see that this technicality of using proper regularization goes from making your action not vary at all to vary exactly how you expect it. In particular, as I mentioned before, they combine precisely with the Green-Schwarz terms, which are, so the field-dependent part of this guy, which is the part which is not invariant, precisely combined with the Green-Schwarz term, which are also field-dependent. And so if the anomaly is cancelled, this is 0, so there is no field-dependent Chern-Simons term, the theory is gauge invariant, and everything's fine. But if the theory we started with does not cancel the anomaly, we have this problem. So we see this is making precise the statement that anomaly are preserved under circle reduction. So now let me start from theory which does cancel anomaly. So this term disappears, and we are left with the one which is not field dependent. Plus we are left with the classical piece, which does not cancel. And if anomalies are, the mixed anomaly and the pure gravitational anomaly are also cancelling, then we can replace the sum of the square of the charge by this guy, and the 9 minus the number of tensor by this guy. So this is the full Chern-Simons action you get after doing the one-loop computation. And it does not receive further quantum correction. So the one-loop result is exact. And this Chern-Simons action comes directly from a prepotential, a normal one, which is cubic, which is given here. And this is the fully corrected prepotential. So from this prepotential, you can read off what the corrections to the coordinate should be. And you see all the correction is appearing in this function delta, which incorporates all the one loop correction. And even more, as I said, because of supersymmetry, the kinetic terms are related to the Chern-Simons terms. So by computing the Chern-Simons one loop, going through the prepotential and then computing the metric like this, we can find the corrections to the kinetic terms. So this is the kinetic terms before the correction, so the classical result. And after including the corrections, here is what you get. Again, everything is included in this delta function. Okay, so now let me switch gears and talk about what implication this has for F-theory. So we want to look at effective action of F-theory on a Calabi-Yau threefold. So it gives you a 6D 1,0 theory. And in order to get the effective action, one uses the M-theory duality. So which says that if the Calabi-Yau is elliptically fibered, you compactify M-theory on this Calabi-Yau, you get to a 5D theory, and then sending the fiber to 0 will lift for you to the 6D case, to the 6D effective action. In practice, this lift, once you want to compute the action, is done by take a generic 6D theory, reduce it on the circle, and then compare with the M-theory result, the M-theory reduction. One should note that the two sides are very different. This circle reduction, you need to include the quantum correction, while the M-theory reduction, only the classical reduction, and then they will match. Well, this is the philosophy. Then we're going to check that it does match. So we just did this case in the first part of the talk. Now let's look at the M-theory on a Calabi-Yau threefold, and in particular, let us look at the vector sector. So the vectors in 5D come from expanding the tree form along 1-1 form, harmonic 1-1 form of the Calabi-Yau threefold, like this. And the Chern-Simons terms will come from the 11-dimensional Chern-Simons terms in this manner, where the coefficients are just given by the triple intersection number of the 1-1 form or of the Poincare dual divisor. Because these are intersection number, they are field independent, they are just numbers. So as we saw, they can only be matched with the circle reduction of a theory that was anomaly free. Because if we started with an anomalous theory, as we saw, we will have field dependent Chern-Simons terms, which is not the case. So all the EFTs from F-theory, which can be obtained in this manner, are automatically anomaly free. So this is one. And now we want to specify to a Calabi-Yau, which is the matching with our setup. We took a 6-dimensional theory which has only abelian gauge field, so it should be smooth, so there is no non-abelian gauge field, and it should have extra section for the abelian gauge field. Then it has to be elliptic fibered for the F-theory for the F-theory limit to work. Then it's known in the literature what is the correct basis of these divisors to lift to F-theory. So the vectors that will lift to two forms in 6D come from the vertical divisor, which are pullbacks of the base divisor. Then the KK photon will come from the 0 section, which is shifted in this manner. And the U1 vector will come from this extra section, which are shifted in this manner. It's called the shear order. Okay, so this basis of divisor is the correct one. Then you can compute the intersection number of these three divisors and plug it into the prepotential. Or if you wish, you're just computing the Chern-Simons coefficients. But it's, let's say it's easier to speak in terms of the prepotential, but it's exactly the same as to speak of the Chern-Simons coefficient. So the prepotential here is given in terms of the Kähler, these coordinates, which are Kähler coming from the Kähler form, expanding it on this 1-1 form. Then if you plug in the coefficient, the intersection number you computed, you will find this form. Where here this circle denotes the product using the intersection matrix on the base. Pi is the projection onto the base, and k are the coefficient of the expansion of the anti-canonical class of the base. So now we have the full M-theory prepotential, and this should be matched with the circle reduction one we just obtained in the first part. And you see that they precisely match if one identify the coordinate in the straightforward way, the metric as well, the Green-Schwarz parameters A and B in this way, and the triple intersection number in this way. These two relations are very well known result in the literature. And this was already mentioned and checked for a couple of examples. But now we see that every term matches with those conventions. So this also justifies, if you wish, the choice, which seems a priori weird of the coordinates we did at the beginning. This is the only choice that makes everything fit together with this identification. But let me point out that for this to work, for this match to work, it's only possible if all anomalies cancel. So the pure gauge, but also the mixed and the pure gravitational. And also if you use the adequate regularization, as I mentioned, if you use the zeta-function regularization, you will have this annoying term, which is quadratic, well, of degree 3, and which doesn't match with the M-theory reduction. Okay. So this brings me to my summary. I don't know how I'm doing on time. I think it's good. Still have 2 minutes. So we looked at 1,0 theories on a circle. We saw that if we use a regularization that preserves 6D Lorentz invariant, then the anomaly shows up as field-dependent Chern-Simons terms, which will vanish if and only if the anomalies cancel via a Green-Schwarz mechanism. And from this, we could obtain the 5D cubic prepotential for anomaly-free theories, and from which we read off the kinetic terms, the corrections to the kinetic terms. Then in the second part, we looked at the implications of this has for F-theory effective action. We saw that because the Chern-Simons coefficients are given by the intersection number, these are automatically anomaly-free EFTs. This leads to anomaly-free EFTs. And then we could match perfectly the M-theory prepotential with the one we obtained from the circle reduction on the condition that all anomalies cancel, and we use the adequate regularization. And then this gives us, as a bonus, the correct identification of the coordinate. And thank you for your attention.
Great. Thanks a lot, Pierre, for the very nice talk. Let us all applaud using our Zoom reaction. Are there any questions for Pierre? So while we wait, I can ask one. So you talked about using polyvelars as a way of regularizing this object. Are there other ones that work as well? Like if I use demreg, would that also fall into this, or?
So there are definitely different regularization you can do. They don't all give you the same result. So okay. There are others than this. There are like you can use the Poisson take or stuff like this. I don't know the one you're speaking about, but they don't all give the correct answer. The correct answer really comes out by asking that it really preserves 6D invariance. Because you see, if you ask 6D Lorentz invariance, you are forced to give up on gauge invariance, because in 6D you cannot have both because of, well, chirality.
But as long as it preserves 6-dimensional Lorentz invariance.
Well, this is the claim.
Okay.
This is going to be the claim.
Okay.
Then we need to check, but I would bet on it, definitely.
Miguel?
Hey, Pierre. So I was just wondering, so the effect you basically described where you just have if you're not careful about preserving Lorentz invariance, then you get basically wrong or non-invariant results in the IR. So you could perhaps, if you do it, you could say that if you do it the wrong way, you could conclude there's some sort of anomaly. The theory is actually not invariant in the IR, where it actually is. It's just that you speak the wrong regularization. Do you think, is it possible that things like this also happen with discrete symmetry? Like if I'm looking at an anomaly of a discrete symmetry, but it's come from dimensional reduction from a higher dimensional theory, could this happen?
Yeah, I know we talked about it once. I think in principle the argument should hold. No, it would be weird that you have even if it's a discrete symmetry, that you think it has an anomaly or when it should not, and vice versa. So maybe then it's more tricky to show it directly, like here with the Feynman diagram. But in principle, this should hold for any type of anomaly. So I would say no, unless you have an argument against.
No, I don't. I'm asking. Okay.
Yeah, but definitely there is definitely much more to look at to this story than just these chiral anomalies, which are pretty easy to see.
Right. Okay, thanks.
Well, if there are no more questions, let's thank Pierre again for this very nice talk.
Thank you.